Okay, so with the assumption that posture balance controls are controlled by the sensory feedback, the feedback information from the joint kinematics, the next step is how we can identify the K. Okay, so for assuming that the joint torques is gonna be a function of state variable, the joint kinematics, and how we can identify the K. Among many possible ways, we will propose to obtain the gain K with the linear regression. So note that your X is going to be measured by the optical motion capture systems and so on. And your joint torques are calculated using inverse dynamics, right? And then with those two measurement and estimated value, you can actually find out the gain K using the regression. I refer the article by Barin. Okay, so to do so, before the very first step is you have to obtain the equations of motion. So how many segments are you going to model the human posture? Maybe the simple single segment could be possible. Since you know that your sensory feedbacks are using the motion information from the sensor located at the head, that like a vision and vestibular, you may want to include more segments, like a 3 segments or 4 segments, including the head. So all depending on your is your model, the segment number of segment model could support your hypothesis. So at least your model, even though it's simple, should should be able to represent the data well. So maybe the first rule of thumb to check this model simplification uh, borderline will be examine the errors between the simplified model and the data. So here, the joint torques are all calculated or estimated through the inverse dynamics, except the ankle joint torque. Assuming that your ankle, the foot is flat on the ground, your ankle joint torque could be directly measured by the ground reaction force, like from the force plate, right? So by comparing your error between the torque ankle and the torque ground reaction force, this shows the error. Like first, a single segment, even though it's simple, greatest error, of course, intuitive. And if you increase the number of segments, errors decrease, but huge improvement with by adding upper limb joints, and then there aren't significant improvement by adding more segments. Okay, so I would say in terms of efficiency, like guaranteeing the model accuracy without the cost of model complexity, I would choose a 2 segment will be enough. But if you would like to examine maybe the influence for the head movement, you should actually definitely include the more segments on it. One thing I'd like to note is, suppose that if I assume the human posture as a single segment, what does that mean? Okay, I have a knee joint here and then hip joint there, but if I made it as a single joint, what that means is joint angle is going to be 0, right? So this is a line. So if joint angle is 0, is joint torque, corresponding joint torque to make the whole body as a single segment also 0? No, because to make this upper segment align with the lower segment, there should be, to compensate the gravity and or the dynamic motion, you should apply the compensatory hip joint torques, what we call as a constraint torque. Okay, so note that if, when you simplify the joint segment, because it's just one of the frequently asked question, like real human segments are this much, your model is too simplified. In that, you should also consider what are the corresponding joint torques assumed that applied here for your model. Okay, so for the first case, let's examine the 4 segment model, and then let's identify the gain K using the linear regression. With the linear regression gain K data, you can also simulate it, and then look at the response from the data depicted as a solid lines and the simulation, which is dashed line. And then you can see it's pretty well represents, right? The head, torso, or the 4 segment joint angles look very well described by the simulation. Since you have a 4 segments, you have a 8 state variable like a theta 1, 2, 3, 4 and corresponding angular velocity. and that will contribute to generate the torques at 4 joints. So you have a 4 by 8, like 32 components for the feedback gain K. So anyway, your simulation and data looked similar. Your proposal saying that joint torque could be expressed by the feedback of joint kinematics might be approved. Then the next step is you should examine the open loop poles and closed loop pole dynamics. So open loop pole, since this is a inverted pendulum, has a mirror image behavior like this, okay? And then how those are stabilized using the feedback. So with the full state feedback, you have a stabilized closed loop pole. Let's examine. All the right half pole has been moved to the left half plane here. Okay, so minus 0.5, minus 0.76. But except the last one. Last one still has a positive rear part, which means unstable pole. Why, even though it has unstable pole, why this simulation looked so good? So that's because you only simulated for a short amount of time. For those short amount of time, your simulation may look good, may look okay, but you should also examine thoroughly about is your controlled model make sense in terms of control perspective. So definitely those unstable poles is not desirable. So either you should find another gain K or to the other approach. So next suggestion is like instead of having 4 segments, maybe I have too many degree of freedom, too many free parameters to fit. So there are redundant solution exists. So that's maybe why I have unstable poles that still shows the reasonable simulation behavior. So I may decrease the number of segments, reduce the system by 2. Upper and lower body. The upper body depicted as a green line and lower body depicted as a blue line. So in that case, your gain number is reduced by 2. By 4, the total 8 gain parameter. Okay, so for the full state 2-segment model, you have a 8 gain parameters, and you can even reduce the model further. Like for the torque 1, ankle torque, maybe the ankle joint angle and ankle joint angular velocity only contributes, okay? And for the hip angle and hip angular velocity, then you can even further reduce the order of the system, then the number of gain. Or maybe you may not need the D control, like you only need a error proportional torques. That's only the P control. You can also reduce the system in many ways. So let's look at the results. So for the full state feedback for the 2 segment, okay, here, data is solid line and the simulations are dashed line, looked pretty well matched with the simulation. And even reduced order, like independent control for per joint, also show the reasonably good match. Okay, and this doesn't work. So that means like proportional only doesn't work. So you at least have those D control components for your joint feedback model. Okay, let's examine the closed loop poles. And closed loop poles all look stable. Okay. However, even though the response itself looks similar for the full state feedback and reduced independent joint feedback, I could see that this value are a lot greater than this value. This dominant pole gets too close to the origin. So what this means is definitely joint torques for the posture control can be expressed by the feedback control. Okay, but the gain is not unique. Okay, there are many gains that could reproduce the observed data. Okay, so human behavior, posture behavior could be successfully controlled by expressed by the feedback control law, and those gains were somewhat arbitrary. Okay, so the hypothesis has been proved. So maybe the next question we would ask is why is that specific gain? Or is there any other explanation for choosing the gain or identifying the gain, etc.? Okay, So I'm going to also introduce other studies about identifying gain in a different manner and put provide a different interpretation for the next slide.